Okay, collisions. There's two types of collision we're going to be looking at. Inelastic collision and elastic. I should have wrote elastic and inelastic, but with both of these, elastic and inelastic collision, we will have conservation of linear momentum. In any type of collision, you will have conservation of linear momentum. But the mechanical energy may or may not be conserved. In one case, yes, it is. In the other case, no, it's not. Mechanical energy is conserved in elastic collision. What does that mean, elastic collision? This is like bumper cars. When they hit each other, you know, they have that rubber on them. They don't stick, they bounce. That's elastic collision. Inelastic collision, that's when they stick together. Like if you have, I was trying to do this in the lab. We had the cart. Remember that cart here? And what did I have at the end of the cart? I know you didn't get a chance probably to look at it. What did I have here? Velcro. I had another cart. Nope. It's supposed to be the same size, or maybe shorter one. Same height, I mean. And what did I have here? Also Velcro. What happens when this one comes and hits this one? Let's say this is not moving, but this is moving. Because of the Velcro, what will happen? After the impact, they stick together. And they travel with one speed. Different speed called V2. Now that type of collision is called inelastic. They're stuck together. Elastic collision, they don't stick together like bowling. When you play bowling, you roll the ball, it hits the pin. Do they stick together? No, they bounce. That's elastic collision. Or if you're playing pool, you fire that ball there and pool, it hits this one. This is the white one, what is it called? Q. And you want to sink in the number 2. You hit the number 2 there. Do they stick together? No. This type is this is elastic. And this type of collision is inelastic. So when they stick together, that's inelastic. When they bounce, they don't stick like bowling, pool, that's elastic collision. In this type, we have conservation of linear momentum. In this type, we have conservation of kinetic energy also. In inelastic, we have conservation of linear momentum. But kinetic energy is not conserved. They do not equal to each other before and after. So you only have conservation of linear momentum. Both of these you have conservation of linear momentum. Again, I should have called this inelastic and elastic collision. Just do them all in one shot. So let's take an example. Take football, take hockey, because they tackle each other in that sport. So we'll take the best team in the world in football, obviously. Which one? New England Patriots. Eagles, just we gave it to them, trust me, they're not good. So anyone listening on my video from a different state, your team is not as good as my team. The Pats are the best. So now we got the New England Patriots and Hightower, big boy, has a mass at least 100, 110 kilogram, about 240 pounds. He's running this way with the velocity of, I don't know, 6 meters per second. You get a small running back, has the ball with him, has a running back, not as big as Hightower, has a mass of 90 kilogram, running with the speed, just started, so he didn't pick up speed yet. Usually the running backs are fast. We'll say 4 meters per second. This is before. Hightower tackles him, that's the before. And this is the after. After the tackle, now the two of them, Hightower wrapped his arm around him. They're stuck together because Hightower has his arm around him. He can't run now. And which way they're going to move? What do you think? I'm not really sure, but I'm looking at this guy as heavier and faster. That tells me, I was trying to show you that picture yesterday, when a heavy one hits a small one, what happens? They move forward. So I have a feeling they're going to move in this direction. I know they're going to move in this direction. But I'm going to pretend I didn't know which way they're going to move. I'll make it that direction. Let the math tell me you're wrong. They're going to go backward. I don't have to think about it. So what is that velocity? Notice Hightower is actually grabbing that running back. That he's holding him. So what kind of collision do we have here? Do we have inelastic or do we have elastic? Did they stick together? Yes, we have inelastic collision. If he bounced off him and missed him, that's elastic. So we have inelastic. What happened to T there? So if it's an inelastic, we only have conservation of linear momentum. That's it. And we'll prove to you that you will not have conservation of kinetic energy. Again, I'm going to define this positive, this negative. I mean positive. Well, they're not moving that direction, so who cares? But to the right is positive, up is positive the whole time. So that before, we have the running back. What was his mass? 90. What was his velocity? 4. What was the mass of Hightower? 110. What was the velocity of Hightower? 6. Is it 6? Negative 6. He's going to the left. We assumed once they tackle, because we know the running backs are fast, maybe they'll push him, or we didn't think about it. We assume they're going to stick together and move to the right. Now, what's the mass once they stick together? 200. It's this mass plus that mass. They're stuck together now. It's one object. And they're going to move with one speed. We'll call it V. Since I define it to the right, that's positive V. Where's my calculator here? 90 times 4 minus 110 times 6. It is negative 300 equals 200 V. So what's the velocity? Negative 1.5 meters per second. Says you are wrong. You assume it's going to the right. The math said negative. So which way they're going to go? They're going to go to the left. So the two players after the tackle, they'll move in this direction. Speed together equals 1.5 meters per second. Let's try another one. We'll take a train, cargo train, carrying stuff in it. This is, so this is the train here. has a mass of 10,000 kilogram. And it's moving to the right of, I don't know, velocity equals what? V1 equals 2 meters per second. There's a little hook here on it. We have another one behind it, not attached to it yet. Has a mass of 12,000 kilograms, a little bit heavier. And to catch up to this, has to be moving faster. Has a velocity, we'll call it V2, that's mass 2, mass 1. Has a velocity of what? 2.1 meters per second. To the right again. Has a hook on it. So what's going to happen as this one collides with that one? The train, they stick together. And now after the impact, they're going to look like this. Suddenly they shrunk in size, but I'm out of paper. So this is M1 and this is M2, and they're going to go in this direction with the velocity V. Is that elastic or inelastic collision? Inelastic. They stick together. That means the initial linear momentum equals the final linear momentum. What's my initial? The mass of the first one, the 10,000 kilogram, times the speed, which is what? 2 to the right, plus the mass of the second one, 12,000 kilogram. Speed is 2.1 equals, what's the combined mass now when you put them together? 22,000 times the velocity V. This number 45200 equals 22,000 V. What is V? So they're going to be moving together with speed 2.0545 meters per second. And by the way, if we calculate the kinetic energy before and after, they will not equal to each other. Let's prove that. Let's prove it. The kinetic energy, initial kinetic energy, should not equal, I'm putting a big not equal, the final kinetic energy. What's my initial kinetic energy? Let's look at the first one. The mass is what? We know kinetic energy is what? 1/2 mv squared. Remember that equation? Better know it for the test in a few minutes. So the kinetic energy for this is going to be what? 1/2 the mass, which is 12,000, times 2.1 squared, plus the kinetic energy for this, which is 1/2 the mass, times the velocity, which is 2 squared. It should not equal, I'm going to prove that, the kinetic energy for this, which is 1/2 the mass, which is 22,000. And what was the velocity when we calculated? 2.0545 squared. Let's see if that's true. And this number I came up with, 26460 on the money. Let's look at that number. That number is 20,000. I'm saying it should not equal. This number is 46430.7. Let's add these two numbers. And it's not rounding error. $46460 does not equal 46430.7. They will not equal to each other. The kinetic energy is not conserved when you have an inelastic collision. No conservation of kinetic energy for inelastic. Now let's look at elastic collision then. Let's look at elastic collision. What's going on now? We can use an example for that. Got it. The World Cup, soccer. What team you want to use? Colombia. Do we have a player on Colombia in particular? Everyone knows Ronaldo. So we'll use the Portuguese, Ronaldo. Not many people don't know Ronaldo. Here's Ronaldo. The little guy is skinny. So his mass probably 70 kilogram. Boy, can he play. When he's running toward the ball, his velocity, he's running in this direction. His velocity is what? Just pick a number. 7 is flying meters per second. 20. Now there's a ball coming our way. Here's the soccer ball. Well, basketballs, you know. Has a mass. It's not that heavy. I would say half a kilogram. If you get hit by half a kilogram, you'll feel it, but the way they're designed, just like a spring, basically. The ball dent on your head so it doesn't kill you. And the ball is moving this direction with the velocity of 30 meters per second. Somebody fired the ball. Now, Ronaldo hits the ball. When he hits the ball with his head here, what's going to happen? Probably the ball is going to go in that direction. God knows what velocity is. We'll call it VB for the ball. And what's going to happen to Ronaldo? Do we know? I'm not sure. Let's assume he's going to move in this direction. We'll call it VR for Ronaldo. I just found out that you can't really, in middle school now, you can't hit the ball anymore. It's illegal. Really? God, my son he was a sweeper. He probably hit about 10,000 balls, and I was to get nervous, like, Joseph, this is not good for your brain. I did that when I was young, too.
I'm practicing with, like, balloons and stuff.
Balloons?
Like
Oh, yeah. I just found out someone said you can't hit the ball anymore till you're like, 13 or something like that.
Positioning down so that when you do are age appropriate, you
Hit it.
understand the fundamentals of how to do it.
So now, is this elastic or inelastic? If they don't stick together, it's what? Elastic. If it's elastic, there's two things you have to deal with. One, conservation of linear momentum. The linear momentum before should equal the linear momentum after. What is my linear momentum before? the mass, which is what? 70. That's Ronaldo times the velocity, which is what? 7. Add to it the mass of the ball, which is a half, times the velocity, which is what? Negative 30. Good. Equals, I assumed, now again, I made the assumption. I don't want to think about it. I made the assumption both going to go forward. The mass of Ronaldo, which is what? 70, times the velocity, which is VR, plus the mass of the ball, which is 0.5, times the velocity, which is V ball. That's 49 minus 15. 49, we're good. Yeah, 49 minus 15 is what? 34 here?
47 is 490.
490, oh, yep. 490 minus what? 15? 475. Equal 7 VR plus 1/2 VB. I don't like the 1/2. Let's multiply everything by 2 to get rid of the half. 475 times 2, 950 equals what? 140 VR plus VB. That's one equation. How many unknowns in that? 2. I'm going to need one more. I got to rush through this because we have our test in 10 minutes. So what's the other one we have to use when you have elastic? Conservation of kinetic energy. Kinetic energy before should equal the kinetic energy after. 1/2 the mass of Ronaldo, 70 times his velocity squared, plus 1/2 the mass of the ball times the velocity of the ball squared, equals 1/2 70 times VR squared plus 1/2 0.5 times V ball squared. Because the 1/2 shows up in every one of them mathematically, if you want to make life easier on you on the calculator, you can drop it out of each one. Mathematically, that's good. You can do that. Why? Because you can multiply the whole equation by 2. If you multiply by 2, there goes the 1/2. So I don't have to deal with the 1/2, keep pushing the 1/2 on my calculator. So what do we have here? 70 times 49. 7 squared is 49. 3430. 0.5 times 30 squared plus 450 What's 450 plus 3430? 3880 equals 70 VR squared plus 1/2 VB squared. I don't like the half. Let's multiply everything by 2 to get rid of that half. And that's my second equation. Now my physics is over. My torture is going to be math. There's my 2 equations. Can you see them? So how do we solve them? Let me write the 2 equations and put the physics away and start dealing with the math. If you look at that equation, can you solve it for VB? What's VB equal to? 950 minus what? 140 VR. From that equation, right? I'm going to use substitution. I'm going to solve for one of them, plug it in. So if I solve for VB, you take this one to this side, becomes a minus. Now let's go to this equation, and every time you see VB, take it out and put that value in place of it. And God help us now. That's VB, and you're going to square it. So I went to this equation, and I said, let's take the 7760 equals 140 VR squared plus, in place of VB, put what VB is equal to, then square it. As I said, my physics is over now. It's all math. How do we solve this? What method we have to do here? Foil it. So let's foil this one. I'll do it quickly. $950 times $950, because I know the shortcut to foiling that. It is 902,500 minus 2 times the 950 times the 140, 266,000 VR, plus, this one keeps dying on me, plus 19600 VR squared, if you foil it. Let's collect like terms. $19740 VR squared minus 266,000 VR. And what is this number minus this? Because when you bring this to this side, it becomes a negative. 902,500 minus 7760. And to make the number smaller, I'm going to divide each one of them . This is 45.33, and this number, let's see what that number, 266,000 divided by 19740, 13.48 VR. What do we have, a quadratic now? Notice by dividing by that number, you shrink the numbers, you make them reasonable, smaller, more manageable. Now, quadratic formula, if you have your calculator that does that for you, fine. If not, I don't have mine. So minus b, that'll be, I'm going to use the quadratic formula there. That'll be 13.48. Plus or minus the square root of 13.48 squared minus 4 times A is 1, C is 45. All divided by 2A, that's 2 times 1. I'm almost done. I know you're getting anxious now. So I got 13.48 plus or minus 0.63 divided by 2. So two solution. One when you put the plus 0.63 divided by 2, 7.06, which is 7 basically, or 6.43. That's VR. Can we find what VB is? What was the equation for VB? VB is 950 minus 140 VR. $950 minus 140 times 7.06. I got negative 38. $950 minus, just double check, 140 times 7 roughly, negative 30, 38, whatever it was. And what's the other one? 950 minus 140 times 6.43. So these are my two values. One of them is not going to make any sense physically. Let's look back and see what happened to that story. The ball is coming this way at Ronaldo. Ronaldo hits the ball. According to this answer, it says, guess what? Ronaldo is going to continue to go in that direction. Speed of 7, just a rounding error. But the ball is going to go which way? Backward, this way, of a speed of 30. The only way that will happen if what? If Ronaldo has a hole in his head bigger than the ball, and the ball just went through it. That's the only way. So you know that answer doesn't make any sense physically. This one, it says, Ronaldo is going to slow down a little bit. Instead of 7 meters per second, it's going to be running what? 6.43. And the ball is going to go forward in that direction of a speed now 49.8, bigger speed. And that makes more sense. If you ever hit a soccer ball, you know that's what happens. You hit it, the ball goes backward, and you continue going. So that's the one that makes sense physically, where this one does not make sense. Yep. By the way, if I use the 7, that would be negative 30 here. So that means no change really. Or just rounding error. I can't do any more examples. We have a test now.